Now we're about to undertake proof by induction for de Moivre's theorem. And when we're doing the proof by induction for de Moivre's theorem, it's enough to quote what's in front of you now, that cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta for all n belonging to the set of natural numbers. So we are now going to look at step 1, and step 1 is show true for n equals 1. So we need to show true for the smallest value of n that we're allowed, which in this case is n equal to 1. Show true for n equals 1. So at the moment what we have is we have left-hand side is equal to cos theta plus I sine theta in brackets to the power of n. So when we substitute n equals 1, we end up with cos theta plus I sine theta to the power of 1. And we know that anything to the power of 1 just stays the same. So that becomes cos theta plus I sine theta. Now we're going to do the right-hand side. So the right-hand side of our expression above is cos n theta plus I sine n theta. And we replace the n, put it equal to 1, so that becomes 1 theta plus I sine 1 theta. And therefore the right-hand side now becomes cos theta plus I sine theta. And clearly for n equals 1, we have now got that the left-hand side definitely equals the right-hand side. So therefore we can now write left-hand side equals right-hand side, shown true for n is equal to 1. Okay, so we're now going to look at step 2 of the inductive process. So step 2, we assume true for n equal to k. Therefore, cos theta plus I sine theta to the power of k equal to cos k theta plus I sine k theta is assumed true. We now move on to step 3 of the inductive process. And step 3 is need to prove true for n equals k plus 1 using step 2 and possibly step 1. Now that's a generic statement which we've been using for all of our inductive processes. So what we now do is we need to write down what we're trying to prove. Therefore, need to prove that cos theta plus I sine theta all to the power of k plus 1 will equal cos, open bracket, k plus 1 on theta plus I sine k plus 1 on theta is true, using the step 2. So what we've done is we replaced the value of n by the value k plus 1, and we have now got to show that the left-hand side will give the right-hand side by using our assumption from step 2. So we're now going to write over here proof and start the proof part of this activity. So first thing we're going to write down is left-hand side is equal to cos theta plus I sine theta to the power of k plus 1. And we're going to use the first law of indices. So what we have at the moment is we have a number to the power of k plus 1, and we're going to break that down into x to the power of 1 times x to the power of k. So therefore, using the first law of indices, the multiplication addition law, in reverse. So this left-hand side is now going to become cos theta plus I sine theta to the power of 1 multiplied by cos theta plus I sine theta to the power of k. Now, the algebra for the laws of indices was just there. I wrote that so that you could relate to it before I bothered working it out. It's not part of the proof. You expect just to do it, know it, and go from there. At this stage, you should spot that by breaking down the power, that you have now got the left-hand side of your assumption in step 2. And that left-hand side, because of this assumption, can be replaced by this expression here. So we can now go to the next line, which is open bracket cos theta plus I sine theta on open bracket cos k theta plus I sine k theta, because we are using our assumption from step 2. We're now going to multiply these brackets out, not doing anything fancy, just multiplying. So we've got cos theta is going to multiply cos k theta. And then we're going to have a plus on a plus, so it's a plus cos theta on I sine k theta. And then plus I sine theta on cos k theta. And then plus I sine theta on I sine k theta. And now we're going to do a tiny bit of tidying up. So we're going to do cos theta times cos k theta. We're going to bring the I to the front, plus I on cos theta sine k theta. We're going to bring the I to the front. Oh, sorry, it's already there, so just repeating it. Plus I sine theta cos k theta. Now, we're going to bring this I out to the front. If we do, we're going to get I squared. So we're going to get I squared sine theta sine k theta. Now, one more bit of tidying up. So this is now going to be cos theta times cos k theta. Now, I plus I squared, because we know from complex numbers that I squared can be replaced by minus 1. So plus I squared becomes minus 1. So I'm going to write minus sine theta on sine k theta. And then I'm going to do plus I, and I'm going to factorize the I out. So I've got, for the next pair, cos theta sine k theta plus sine theta on cos k theta, close bracket. Now we need to go and look at the trigonometric section of your book, of your formula and tables book. And if we look at page 13, on page 13, you've got all the formulas, but they use a single letter, letter A, which means the angle is fixed. Whereas here we've got two different angles, theta and k theta, which means we need a page which has got angles which use A and B. So we turn to page 14 of the formulas and tables book, and we are now looking for a formula which matches this. So my guess is I'm looking for a formula which reads cos A times cos of a different angle, so it has to be B, minus sine A sine B, because I'm designating that A is theta and B is k theta. And indeed, I can do the same thing over here. I'm looking for a formula which is cos of A on sine of B plus sine of A on cos of B. Now let's focus on cos A, cos B minus sine A, sine B. And you need to look at your formula book, you need to look at page 14, have your formula book very near where you've got this written. And I'm hoping that you spot that page 14, the very top on the left-hand side, you will see that this is going to be equal to the cos of A plus B. So I can now write the next line. So it's going to be the cos of, well, A is theta and B is k theta. So we have just rewritten all of this down into this single answer, which is beginning to look like what we need on the right-hand side. So all I have to do now to make the formula match the green above is to factorize out the theta. So all I've got to do is factorize out this theta. And I'm going to factorize it out, and I'm going to write it on the right hand side. So this line now becomes equals cos. So if I factorize out the theta and write it on the right hand side, I'm left with a 1 plus a k. Now I'm going to make the assumption that that's probably going to be true for this one as well. 1 plus k on theta. Well, let's see if this is true. So I'm looking at cos A sine B plus sine A cos B, and that formula is at the top of page 14 on the left hand side, and it's second one down. Now it takes a bit of looking, but you see that this does equal the sine of A plus B. And if you're not sure, let's just copy it out from the formula book in blue and see whether it matches the one above. So we've got sine A from the formula book, cos B, plus cos A, sine B. And clearly the sine A cos B is here, and the cos A sine B is written on the left hand side. So it does match, it's just a different way round. So now I can put in here plus I on the sine of A plus B. Well, A is theta and B is k theta, and then it brings us down to the next line. So tidying this up now for the last bit, I can rewrite this as cos of k plus 1 on theta plus I sine k plus 1 on theta. This clearly equals the right hand side up above. So I can now write shown true for n equals k plus 1 using step 2. And then I can finish this proof off by writing down step 4, proof follows by induction.